Hey everyone, today we're going to be talking about something called L'Hopital's rule, and this is going to be a way of using derivatives to help us evaluate some more complex limits. So we're going to start with a quick way or a quick review of evaluating limits kind of the old way, and then we'll talk about a new method that will work for certain limits. So if we look at number 1, we have the limit as x approaches -2 of this function here. Now, when we talked about evaluating limits, we know that the first thing we would always try to do is just plug in the value into our function. Now, in this case, we're going to get into trouble pretty quickly here because if I plug in a -2 for x, I'm going to get 0 in the denominator. So I need to do something else. This is where we had those other methods, such as factoring, or multiplying by a conjugate, or kind of killing off some of the fractions. So here factoring seems like a good option. So I'm going to go down here and rewrite my function, and then I'm going to go ahead and factor the numerator. So let's see, you have x plus 1 times x plus 2 all over x plus 2, and then I notice I can cancel that factor x plus 2. So this limit is the same as the limit as x approaches -2 of x plus 1. Now I can just plug in my -2 for x, and -2 plus 1 gives me a -1, and that's the value of our limit. Now for number 2, I'm going to have the same issue. If I try to plug in my value into the denominator, I'm going to have a 0 in the denominator, so I need to do something else. For these types of problems, this is where we went and we multiplied by the conjugate. So I'm going to multiply by the square root of 1 plus x plus 1 on top and bottom. And then we'll see how this goes. So if I have the square root of 1 plus x times the square root of 1 plus x, that's going to give me 1 plus x. My middle terms are going to cancel out, and then I'm going to have -1 when I do a -1 times a +1. Now on the bottom, I have this whole thing, x times the square root of 1 plus x plus 1. So on top, my 1 minus 1 is going to cancel out. So I really have x all over x times the square root of 1 plus x plus 1. Now I can cancel the x from the top and the bottom. So my original limit is going to be equal to the limit as x approaches 0 of 1 over the square root of 1 plus x plus 1. And now I can go ahead and plug in that 0 for x. So that's going to give me the square root of 1 is 1 plus 1 on the bottom, so this limit is equal to 1/2. So that was our old way of evaluating these limits. And like I said, L'Hopital's rule is going to give us a new way of being able to evaluate certain limits. So here's how it goes. L'Hopital's rule says if you try plugging in your number to a limit and you get either 0 over 0 or you get infinity over infinity, then you can take the derivative of the numerator and denominator separately and try again. And you can repeat this process until the limit works. Now we'll talk a lot about what that exactly means. Now the important thing here is I can only use this rule if I get 0 over 0 when I try to plug in, or infinity over infinity. If I get any other form, then L'Hopital's rule will not work. So let's just use this example to go through. If I first try to plug in 0 for x, I'm going to get sine of 0, which would give me 0 over 0. That's what we call an indeterminate form. I'm just going to write that down because you might see that language. Indeterminate form. If I plug in and I get 0 over 0, L'Hopital's rule says, hey, we can try again. And here's what we're going to do. We're going to say now we have the limit as x approaches 0. We're still finding a limit, but L'Hopital's rule says take the derivative of the numerator, So derivative of sine is cosine. So up top I'm going to have cosine of x. On bottom, the derivative of x is just 1. So really, this is equal to the limit as x approaches 0 of cosine of x. And now if I try plugging in 0 for x, I get cosine of 0, which is equal to 1. And we're done with the problem. So again, L'Hopital's rule is just giving us a way of calculating a limit using derivatives. So let's go ahead and try a few more. Probably won't do all 4, but we'll try a couple, and then we can always look at a couple back in class. All right, so let's look at number 1. And again, you'll notice number 1 is the same problem that we did up here using algebra. So let's see how L'Hopital's rule would apply. All right, so first thing we have to check that we actually have one of these two forms when we try to plug in. So if I plug in a -2, I'm going to -2 squared is going to be 4, plus 3 times the -2 is -6, so 4 minus 6 is -2, plus 2 gives me 0. On the bottom, if I plug in -2, -2 plus 2 is 0. So that tells me I can go ahead and use L'Hopital's rule. So what that means for us is this is equal to the limit as x approaches -2. Now I'm going to take the derivative of my numerator. So I'll have now 2x plus 3. On the bottom, my derivative is just 1. So I have the limit as x approaches -2 of 2x plus 3. And now if I plug in -2, 2 times a -2 is -4 plus 3 gives us a -1. So either option for calculating that limit is fine. We could have done our algebra with factoring, or we could use L'Hopital's rule. We're going to get the same answer. Let's look at number 2. All right, again, this is the same problem as 2 above. So the first thing we always have to check is it one of these indeterminate forms? So if I plug in 0, I get 1 plus 0 is 1. Square root of 1 is 1 minus 1 is 0. On the bottom, if I plug in 0, I have 0 over 0, and we can use L'Hopital's rule. So I'm going to take the derivative. The limit as h approaches 0, or excuse me, x. Now, the derivative of this is really 1 plus x to the 1/2. So I'll have 1/2 times 1 plus x to the -1/2. The derivative of the inside is just 1. And when I take the derivative of -1, I get 0. And this is going to be all over the derivative of x is just 1. So let's go ahead and simplify this. We've got the limit as x approaches 0. Really we have, let's see, 1 over 2 times the square root of 1 plus x. So now we're going to try plugging it again. If I try plugging in 0, I get 1 plus 0 is 1. Square root of 1 is just 1, so this limit gives me 1/2. So in this case, I actually think it's way easier to do L'Hopital's rule. There's a lot less of that algebra involved. All right, let's do number 4. All of these have worked. We've only had to use L'Hopital's rule once. Let's try number 4 because I think that may not be the case. Now this one's different because we have x approaching infinity here. Now if I think of plugging in infinity for x, I know that my numerator, I don't want to put equal, is going to get infinitely large. So that would be infinity. Same here, if we could think about plugging in infinity for x, that's going to get infinitely large as well. And so now we do have, again, that indeterminate form. So L'Hopital's rule says to go ahead and take the derivative of the numerator. Well, that would be e to the 2x times 2 because of the chain rule. And on the bottom, we would have 4x. So again, we think of plugging in infinity. This obviously is still going to get infinitely large. And if we could think of multiplying 4 times infinity, that's still going to give us infinity. Since we're still indeterminate, we can use L'Hopital's rule again, which means take the derivative again. So the limit as x approaches infinity. Let's see, we have 2 e to the 2x times 2, and now we just have all over 4. So I'm going to simplify this a little bit. This is the limit as x approaches infinity. Well, my 2 times 2 on top and my 4 on the bottom are going to cancel, so e to the 2x. And now I can see this limit is just going to be infinity. So this is an example of where we actually apply the rule 2 times. All right, now something to look out for with L'Hopital's rule is just because we can use it doesn't mean we should. So for example, if I look at option 1 and I think about plugging in infinity, right, that's going to give me this indeterminate form of infinity over infinity. So L'Hopital's rule says I could take the derivative of the top and bottom. So let's see, I would have 12x squared plus 10x minus 6 all over 12x cubed plus 18x squared minus 14x. And if I plugged in infinity for my x's, I'm still going to get infinity over infinity, so I could go again. The limit as x approaches infinity of, let's see, I have 24x plus 10 all over 36x squared plus, let's see, 36x minus 14. Right, plug in again. I still have infinity over infinity. So now I would do limit as x approaches infinity, and I would have 24 over, let's see, 72x plus 36. Now, if I think of plugging in, I'm going to have 24 over some quantity that's infinitely large. And so that quotient is going to go in the limit to 0. So L'Hopital's rule will, in the end, get us to an answer. And again, this is because we have 24 over an infinitely large number, so if I think of dividing that, that quotient is going to tend to 0. However, that was a lot of work for a problem we actually already know the answer to. When we're looking at x approaches infinity, right, we said we're looking at the end behavior. We learned this in chapter 1. So we said we only cared about the highest power in the numerator and the denominator. So I have 4x cubed over 3x to the 4th. Since this is bottom heavy, we know that the limit is 0. And so using an old method here was actually way more efficient because we didn't need to go through all of this calculus to find that limit. So we want to make sure we're being smart about when we use the rule and when we don't. All right, last thing is mistakes to avoid. Once people learn about L'Hopital's rule, they want to use it all the time. But here's where we have to be careful. We always want to check. Remember, we talked about these two indeterminate forms. We always have to make sure we have one of those forms before we use the rule. So in this case, if I look at this problem and I think about plugging in, on top I'm going to have 1. On the bottom I would have 0. I want to make a note that we cannot use L'Hopital's rule here. Right? Because this is not 0 over 0 or infinity over infinity. So here's where we have to use our old methods, right? And again, if we think about this, we know there's a vertical asymptote at x equals 3. So if I'm thinking graphically, I look like this. Now, because my numerator is positive and I have an odd degree, we know our function is going to look like this. So now the limit as x approaches 3, because those limits don't exist on either side, we would say the limit does not exist because the limit as x approaches 3 from the left of 1 over x minus 3 is not equal to the limit as x approaches 3 from the right of 1 over x minus 3. So again, just be careful that you're always checking whether you have one of those indeterminate forms before you apply this rule. All right, that's it for this video. See you back in class. Thanks.